So the other day we looked at translations with functions and more so just linear equations, sometimes with zigzags to them. But today we're going to look at our quadratic family. So kind of review on our quadratics. Our quadratics are just with an x squared rather than just an x, right? Because the x is just our linear equation. So our parent function is the most basic quadratic. It's y equals x squared. Okay, and I want you to graph that on your calculator. I'm going to go ahead and make it over here by making a table, an xy table. So I'm going to use 0. So if I plugged in 0 for x, 0 squared is 0. So right on there. If I plugged in 1 for x, 1 squared is 1. All right. If I plugged in negative 1 squared for x, negative 1, I'd get also 1. Okay, so that's kind of neat. All right. So take a look. If I put in 2 for x, I would get 4, right? 2 squared is 4. What happens if I put in negative 2? What do you think? Oh, it's also 4. Cool stuff. All right, so 2, 4, negative 2, 4. And also if I did 3, it'd be 9, and negative 3 would be 9 as well, right? It makes what we call a parabola. So I'm going to get this guy kind of curves up. Boom, curves up. We call this guy a parabola, right? Parabolas are graphs of our quadratics. And do you remember any of our terminology with our quadratics? Well, if you notice, all parabolas are symmetric. So we have what we call, if I cut this guy in half, we call this guy the axis of symmetry. So the axis of symmetry is basically x equals whatever it cuts in half. In this case, it goes through 0 on the x-axis, so x equals 0 for this guy. And then our most familiar point that we need to know, this point is super important, is the part, it's either the minimum or the maximum point, right, where it starts going back up or going back down, right where that kind of axis of symmetry is at. And we call that guy the vertex. So that's important that we know that, the vertex. Okay, with translating our graphs, that's what we're going to pay attention to, is that vertex. Back in the day, we used to calculate the vertex by taking x equals negative b over 2a, and then plugging that back in to our equation, our quadratic, and finding y. We're not going to calculate the vertex, but we just need to know what the vertex is. So moving on, let's take a look. Okay, so we got the black graph, y equals x squared. What is the equation of the red graph, you think? Well, I bet we could do this because even though it's a quadratic, it still kind of has a y-intercept, right? So if I look at the black graph, its y-intercept is 0. So that's why there's really a plus 0 here, but we don't see it. So I just moved down 1, 2, 3, 4. I moved down 4. So how do you think that's going to change your parent graph equation? So the black one was y equals x squared. So our red one must be y equals x squared. It went down 4, so minus 4, just like that. Pretty easy if it moves up and down, right? You just put it at the end and went down 4, minus 4. And this next one, it went up 1. So what do you think? Oh, yeah, plus 1. Not too bad. Okay, when it gets moving left and right, that's when it gets a little bit trickier. But the nice part is it's the exact same thing of our translation form from the other day when we dealt with functions. Remember how this h represented how it moved in the x direction, whether it moved left or right? And it's kind of the opposite way, right? And the k was the y direction, or basically almost like our y-intercept sometimes, if it's going right through the y-axis. So the same thing works with vertex form. Why do we call it vertex form? Well, vertex is for quadratics. And vertex is because the HK actually happens to be our vertex in this case. Pretty fancy. So if I go, well, let's actually write this out. So instead of having the f of x, it's going to say y equals, so instead of saying f of x minus h plus k, we're going to get rid of the f. We're not going to have a function. We're just going to say x minus h. But what do you think I should put with it? Yeah, a square, right? Because it's a quadratic, and then plus k. That's the only difference. And like if you like the k on the other side, remember you could always minus the k to the other side. I don't like doing that, but you could have y minus k equals x minus h squared. Okay, so either way, it depends. I probably use the green, especially if I'm going to graph it. So going back, if I looked at that last guy, just by looking at this, I could tell the vertex, because this is really like x minus 0 squared, and this guy is, the plus k is negative 4. So my hk, my vertex, was really 0, negative 4. That's the vertex. So it works out nice. All right, let's use this now to help us out. So let's write an equation for the red guy. So the black ones are y equals x squared. So the red ones is going to be y equals, so x minus, so remember it's the opposite. It's not, even though it went right to, it's not plus 2, it's x minus h. So, and the h is 2. So x minus 2 squared. And did it go up or down? No, there is no plus k. So the vertex in this case is 2, 0, that hk, right? Same thing over this next one. Y equals x minus, now it went 1, 2, 3, 4 to the left. So left 4. So really it went negative 4, which makes it x plus 4. Okay, it's kind of, remember that's kind of backwards. The x's are kind of backwards in that case. So it's basically the same thing as our function form, our translation form from the other day, except we have the square with it. That's the only difference. Okay, now it can move in two directions. So let's try to rock this quickly. So we got left 2, so negative 2, and it went up 2. So we got y equals x minus negative 2, which is really plus 2 squared, and then up 2 plus 2. There we go. Over to this next one, y equals 1, 2, 3, 4. Went right 4, and it went down 2. Down 2. So that would be x minus 4 squared minus 2, because it went down. And remember, it's called vertex form because this is my vertex. 4 for the h, negative 2 for the k. That's my vertex, 4, negative 2, right there on my new parabola. All right, pretty fancy. All right, so it says if you're asked to solve an equation that has a square, like x minus 3 squared equals 4, you're really looking for the intersection of two graphs. Well, anytime you're solving an equation, something equal to something, and you're solving for an x, you're looking for the intersection of two graphs. And what I mean by that is, here's one graph, and here's another graph, right? Because it's like a system of equations, like y equals x minus 3 squared and y equals 4. So most of us like to do that algebraically rather than by graphing, but let's look at it on a graph for a second here. So I got my y equals 4, and then we got our y equals x minus 3 squared. Well, and it's just like a system. The solution is where they intersect. So in this case, x equals 1 and x equals 5. It's got two solutions. Well, what if I wanted to solve that guy algebraically? So this red stuff's important. Anytime you're involving squares, you need to remember that when you take the square root of both sides, there are really two answers. And what I mean by that is, for example, x squared equals 9. Well, what could x equal here? Well, x could equal 3, right, because 3 squared is 9. And x could also equal negative 3, because negative 3 squared is also 9. So when I try to solve for x, get it by itself, the inverse of squaring is square rooting. And whatever I do to one side, I do to the other. So the square root and the square cancel each other, and x would equal not just 3, but we say plus or minus 3. It's a positive and a negative. So when I go over here, to get rid of this square, I would square root. That's the inverse. Whatever I do to one side, I do to the other. So those cancel, and I'm left with x minus 3 equals not just 2, but plus or minus 2. So when I add that 3 to both sides, I'm going to get two answers. I'm going to have to take 2 plus 3 and negative 2 plus 3. So I should get x equals 5 and 1 there. Okay, so a lot of times you're going to get two answers for these. Sometimes you won't. Sometimes you might get one or none, but a lot of times you get two answers. That was a kind of a nice answer, but sometimes they're not so nice, right? If I take the square root of something that doesn't have, it's not a perfect square. So in this case, would I square root right away? No, because of this plus sign, we don't want to square root right away because I can't square root each of those individually. It doesn't work that way. So always bring everything else over to get your square by itself. So then I'd have x minus 4 squared equals 8. Then we can take the square root to get rid of that square. So I get x minus 4 equals plus or minus. Okay, let's not use decimals. And let's simplify. So how do I simplify the square root of 8? Remember, I look for perfect square factors. So like 4, 9, 16, 25. I'm looking for something that goes into 8 that's a perfect square. Well, 4 is a perfect square. So I'm going to break 8 into 4 times 2. So the square root of 4 times 2. So really, I'm going to take the square root of 4 times the square root of 2. And what's the square root of 4? 2. So 2 root 2 is the simplified form of the square root of 8. So I'm going to write that instead. So instead of writing the square root of 8, I'm going to say 2 root 2. Because I broke it into 4 times 2. The square root of 4 is 2. And the square root of 2, we just leave because we can't do it. And now let's finish it out. Add 4 to both sides. So my answer would be x equals, well, to make this a little bit nicer, we're going to put the 4 in front. Okay, so we're not actually going to add because I can't. These are not like terms. They'd both have to be root 2s to combine them. So I'm going to say 4 plus or minus 2 root 2 for my answer. That's how I want to write that. Don't write it like this. Don't do plus or minus 2 root 2 plus 4. Don't write it like that. Okay? Put the plus or minus in between them. It looks cleaner. And that's really all there is to it. Okay, so remember, when you get the radicals, don't do decimals. Simplified radical form, we need practice with that. And then when you write it, just like I did for that answer in the end there.